Control System Society student chapter. So our first talk will be given by Meera here. So let me introduce her. So she joined in the year 2021 and her area is development in cyber physical systems. Now, let Meera take the stage. Meera, over to you.
Good afternoon, everyone. Welcome to the first CSS Scholar Talk presented by this IEEE CSS GSAC. So my topic is dual layer security via fractional complex Lorenz system. This is the paper I recently published in IEEE Access and the citation details are given. So from the title, you might have understood like it is about some security approach. Okay, so why do we need security? Basically, the data like some, for example, space data, they asset. So the satellites and the missions generate the critical information for defense, research, and communication. If these data are intercepted or altered, then it can affect even the national security and the mission success. So that we need a mechanism that could that will be resilient to all these kind of any adversaries action. We will see what are the traditional security methods are available. One way is about the like doing encryption through the cryptography methods. So what cryptography will do is it will lock the data with a secret key, which means whatever the data you are giving, that will be formed to like change to some other format with the use of the key and the dedicated algorithm. And second approach is steganography. This steganography approach hides the data inside some other medium. That some other medium can be anything like image or video or whatever, so that the resultant object will look like exactly like the cover medium, which means visually there won't be any change. Like visually, no one can understand something hidden behind. Okay? For each approach has its own strength and weakness. In our approach, we are going to combine these two to enhance the security. So in my approach, it will be like first layer will be doing the cryptography part. It will take the keys generated from the chaotic system and then that will be encrypted using the algorithm called AES, that is Advanced Encryption Standard. And I applied this on the satellite images. And the second layer will be steganography. It will hide the encrypted image, which is output from the first stage on the another cover medium using the dedicated steganography algorithms. For example, LSB, DWT, and spectrum based steganography methods. This is my proposed architecture. So you could see the first here we have to generate the key for encryption, and I have used this keys for two like cryptography also and steganography also. So the key I'll explain this in the upcoming slide. So this is the approach, like input at the transmitter side, we have the input image. First stage, it will be encrypted, and the encrypted image will go to the embedding stage. Embedding is the steganography approach. There, on the cover image, the encrypted image will be embedded using any like LSB, DWT, or SS. And that's how we are generating the stego image. It's the word used for the output of the steganography. And then this Tego image will be transmitted over the communication channel. At the receiver, first we have to extract our data which is hidden behind. So that inverse operation. If you are using LSB, then there is a receiver side also the same LSB extraction will happen, and then that extracted image will undergo decryption, and thus we are reconstructing our original image. So first we'll see what is chaos, because we have seen we are generating a chaotic based activity. So first, the chaos is a nonlinear dynamical system which exhibits the extreme sensitivity to initial condition, which is popularly known as the butterfly effect. The dynamics of the system will be deterministic, but its trajectory appear random and unpredictable. So such systems will generate a random like sequences, which is ideal for the encryption keys. Here keys mean encryption keys. And let's move to the fractional order system. This fractional order system provides richer dynamics and additional degree of freedom for system modeling and cryptography. Next, complex chaotic systems. These systems are producing a higher dimensional trajectories, which means the system state will be in the represented as a complex variable, and then it will give a more unpredictable trajectories with the enhanced randomness for secure key generation. In our we are using this fractional complex Lorenz system for generating the key. So this is the system equation of the fractional order complex Lorenz system, which are represented as a fractional order derivative. So here x, y, z are the system state, x and y are complex and z is real, and a, b, c are the system parameter which will decide the chaotic and alpha is the order of the F4 derivative. Okay. So after applying the complex variables on the particular, we are getting the decomposed system. So the three-dimensional like system will is decomposed to a five-dimensional one. Next, my objective was to improve the complexity of the system. Okay. For that, I have taken two performance metrics of the chaotic system. One is Lyapunov exponent. So the Lyapunov exponent will basically quantifies the amount of chaotic behavior by the system. Okay. So it is the rate of change of convergence or divergence of the nearby trajectories of the chaotic system. So this is the equation for computing the Lyapunov exponent. And second one is the Kaplan-Yoke dimension. This Kaplan-Yoke dimension, which is basically quantifies the fractal dimension of the chaotic attractor. Okay. So I didn't go much into this because considering the audience. So this is the equation for like computing the Kaplan-Yoke dimension. First, using the Lyapunov exponent, which means like the if the system exhibits the higher Lyapunov exponent, then we can conclude that that is a complex chaotic system. And this Lyapunov exponent also system dynamics it will change. If we are having a three-dimensional system, it will exhibit three Lyapunov exponent, and if we have a five-dimensional system, it will exhibit five Lyapunov exponents. But for the system to be chaotic, one at least one exponent should be positive. So that's our criteria. So if that positive Lyapunov exponent, how much it is higher, based on that we are deciding the behavior, the complexity of the chaotic system. Second one is the Kaplan-Yoke dimension. Based on this, like a higher value of this Kaplan-Yoke dimension will give us a diverse range of P. So by considering these two values, we are generating an objective function for optimization, that is Fi of exponent and inverse of the Kaplan-Yoke dimension. And we have to consider these things based on the chaotic system point of view. So first Lyapunov, at least one Lyapunov exponent should be positive. So lambda 1 is greater than 0 and other two will be near to 0. So we are making it approximately equal to 0 and remaining two values will be less than 0. So based on these constraints, we simulated we have done a multi-objective optimization using sequential quadratic programming, and that's how we have done a numerous simulation. But sometimes the values we got for 10 simulations are listed here. So we could see like what are the for which parameter values we got the maximum lambda and maximum DKY, that is there. So the maximum lambda we obtained was 1.626 and maximum DKY was 3.135. So these are the 3D phase portraits time domain response of the proposed system. Here we could see like x1 of t, x2 of t, y1 of t, y2 of t, and z of t. For our application, we have taken x1 of t for the generating the key, but it depends on the user perspective. They can choose whatever the signal or whatever the combination they want. So this is the mechanism for generating the chaotic based ASCII key. So from the chaotic signal generator, we got our chaotic signal. We have chosen the next one, and then we have to sample and quantize. That quantized value is given to the algorithm called SHA-256. It's a hashing algorithm which will generate a fixed uh, like length of digest. And then we are getting a chaotic based ASCII key. Actually, this work was published in IEEE Control System, Indian Control Conference, year 2023. Using this approach, we are generating the keys. Next, I'm using AES encryption. We have several encryption mechanisms. Like in this we have different symmetry key encryption algorithm. Symmetry key means at the transmitter and the receiver, we will be using the same keys. So AES is one of the algorithms. Similarly, we have several like DES, triple DS, Blobfish, and AES. This is the advanced one. It's a symmetric block cipher algorithm standardized by NIST in the year 2001. It's a block cipher algorithm, which means whatever the input we are giving, that will be divided into blocks. That blocks will be 128 bits data block, and the key size will be varied. It can be a 128 bit, 192 bit, or 256 bit keys. And ensure the confidentiality, this algorithm is using substitution and permutation for confusion and diffusion. Actually, confusion and diffusion are the main thing which will be performed in the any encryption scheme. Here we are performing substitution and permutation. So this the steps that is followed in the AES algorithm. First one, key expansion. We have like inside AES we have several rounds. So for each round we have to generate the round keys based on the input key we are providing. So first key expansion will be happen. Then initial round, the round key that is generated will be XORed with the first block. I'm just considering one block. Okay, so first block it will be XORed, and in the main round also it will also depend upon the key size we have taken. It might be some 9 or 11 or 13. Accordingly, whether we have taken 128 bit or 192 bit or 256 bit. First step is substitute byte. So here we have a specific matrix called substitution box. It's a 16 cross 16 matrix. Based on the input pixel value, it will change. It will take the corresponding values in the substitution box. Then shift rows. It will do the cyclic shift and mix column mixing for diffusion, and then there are final. It will be adding round key, which is the resultant will be XORed with the round key. So these operations will be happening for the 9 rounds using the all the round keys, and then the final round it will be except the mixed column, all other 3 steps will be followed. Now framework we are using, as I said, it's like optimized FO complex Lorenz system is used for encryption. And encryption in this block cipher algorithm also we have different modes. So we are using cipher blockchaining mode, which is CBC mode with a random initialization vector. So actually we are using this for protecting the algorithm, protecting the mechanism from the CPA and CCA attack. That's how our ciphertext will be very highly random, and it is other statistics cryptographic perspective. Next about technography. So we are using 3 technography. One is least significant data. What it will do is we have a cover image. That cover image is of our interest. We can take any image. Each image will be like types of pixel values. Every pixel values will be there. No? So in that pixel value, the LSB bit will be replaced with our input value, input image. Okay, that's how it is doing the because if we alter only the LSB bit, visually we cannot see any change in the resultant image. So that's why it is very simple. It offers high fidelity and imperceptible, providing an imperceptible changes. Then DWT, that is discrete wavelet transform. Here, the image will be decomposed into frequency subbands. So, in which in the our data, the secret data which we want to embed will be embedded on the high frequency subband. That's how it provides better robustness against compression and noise. Next one is stretch spectrum based technique. Here, our input data will be spread across a wide range of frequency using the chaotic sequence. That's how it is resistant to detection and tampering. So, in our framework, we are embedding the encrypted image on this cover image using these three approaches, and the cover image will look unchanged, but it will contain our hidden data. So this image I have taken for my application. So it's a rover image collected from Chandrayaan 3, the original image, and it is encrypted using the AES and chaotic based ASCII. So the encrypted image we can see like a kind of a corrupted form, and then we are getting the this encrypted image. Then cover image. Cover image, it's our aerial view of our amphitheater. Then this encrypted image is embedded on the cover image. That's how we are getting our stego image till the transmitter part over. And at the receiver, we are first extracting using the corresponding steganography approach. That's how we are getting this extracted image. This extracted image will be given to the decryption part, AES decryption. That's how we are reconstructing our original image. Next about the so visually we have seen what are the changes happening, but cryptographically and technographically, what are the performance we can measure? Performance metric we have to measure that we'll see. First one is information entropy. It measures the randomness of the pixel distribution in the encrypted image. The ideal value of the this value should be close to 8 for the 8-bit image. Okay. And next one is correlation coefficient. It will evaluate the correlation between the adjacent pixels. It should be close to 0 because the adjacent pixels in the encrypted image should not have any correlation. Then mean absolute error. It's the average absolute difference between pixel values of plain and the cipher image, like that mean squared error, PSNR, the number of pixel NTCR, number of pixel changes rate, which means one pixel value in the plain image, if it changes, then how my encrypted like encryption algorithm is able to produce a result. That will be measured by this NTCR and USCA. Next, histogram. It's a distribution of pixel values. Generally, the histogram of the encrypted image should be flat, like uniform distribution. So these are the metrics I obtained for the image I have taken, the rover image I have taken. So information entropy is the like to also I am getting maximum value. Then these are the histogram of original image. Here, this is a pixel intensity value distributed, and then we could see like a uniform distribution for the encrypted image. Then this thing presentation of the correlation analysis. So for the original image, the pixels are highly correlated, so that we are getting the all the pixels in the diagonal direction. And then for encrypted, these pixels are scattered. Next, we have to compare how my encryption algorithm is better with the other mechanism. So these are the space. Actually, this key space means how much possible keys whether the particular encryption scheme can produce. So I am using the chaotic based ASCII key, right? So based on that, if you compute the key space of that, it will be like 2 power 700. So there is an attack called brute force attack, which means it will try or in that attack, what they will do, no, like they will try all possible combination of key, and then they will try to decrypt the algorithm. Means if they know the what algorithm is, if they doesn't know the key, then they will try all the possible. But the threshold for finding the key is 2 power 100. But we are getting like 2 power 700, which is much more greater. And then other values like to check the other values, we have taken some standard images that are already they used in their existing approach, pepper and baboon images. So in that values also our algorithm performs like gives higher values. Sorry, these are the like some steganography performance metrics for different steganography algorithms. Next, this is histogram analysis for the steganography part. As I told, there won't be any change in the stego image generated like at the output of the steganography stage. So this one is like giving you the histogram analysis, so that like first one is the histogram of cover image, and second image is histogram of the stego image generated using LSD, DWT, and split spectrum. So we could see there is no pixel values changes in the cover image and the stego image. Then these values are also like we have taken the standard images and compared with the existing algorithm. So like these algorithm, this approach we can use in secure satellite communication, defense, aerospace, medical image transmission, and resource constrained environments such as IoT and all. So these are like about the conclusion. We are used chaos plus cryptography plus technography for providing a strong security, and our method secures satellite data like the image collected from Chandrayaan 3, and it offers double protection by adding the encryption and embedding. That's how it is resistant to the modern cryptography and steganography attack. In future, this will be implemented on hardware to for the real-time space missions. So once again, this is my the paper. Any question? Yeah.
You were talking about complex series. Basically, that complexity
It is about
and complexity or less complexity.
it is in the point of view of cryptography complexity. We need a complex key and a diverse range of key. So we are claiming that this chaotic system will be complex if it provides maximum Lyapunov exponent, and the like decay y is maximum, then it gives the diverse range of key. That's how we are concluding these two.
More complexity,
Better key for encryption.
why uh,
What? F-weighted should be minimized because that's why I have taken the inverse of this 1 by lambda and decay y. So this will be minimized to get the maximum value. But actually, since we are using a multiple layers, it will more like power time consuming. But like we have to compensate on both, like security, how much security we needed, and how much efficiently we can. No, like hard. No, we didn't do it. No, like that part we didn't reach yet because it will be done in the future. Like now, currently we have worked on the only simulation level.
Online, or you can change the existing.
ഇല്ലില്ല ഇവിടെ one is will control.
So Meera, thank you for your insightful presentation regarding encryptography and all. So this is our first student lecture series. Invited from our research scholar. So I request our computer society students to give a few more.
First of all, on the behalf of IEEE Encryption Society, so first of all, I would like to say a big thanks to Meera for the wonderful talks related to cryptography. I hope that everyone understood a basic and then more detailed knowledge about the cryptography, analysis, and all those things. So this is our starting talk. So we hopefully can continue this kind of talk series for the upcoming months also. So, and first of all, thanks to Meera, and then without you, we can't make this talk a successful one. So, big thanks to all the audience, those who are present here, and I hope that this continued support will be happen for the upcoming events also. Thank you.